Hello everyone and welcome back to the channel. In this video, I want to talk about page buffers and the current state of my implementation. So far, we have learned a lot about indexing and how I store the B+ tree nodes on the disk. In this video, we will look for a solution to store database objects or rows into the disk as well. As always, note that none of the topics in this video is fully implemented yet. There might be some changes in the future, so make sure to follow the channel and the playlist to get updates. Before we begin, I want to mention the elephant in the room. The voices used in this video is generated by AI, mainly because I was looking for a faster way to create these videos. So let me know how it feels by the end of this video. Let's begin by understanding what a page is, in my view. Imagine you have a book where you write a story down in it. To begin your story, you start from a single page. The moment you want to write the first letter, a complete blank page exists, no matter how much you want to write to it. You can imagine this in a Word document, or how we traditionally had to put a single blank paper into the typing machine, no matter how many words we would fill in that page. The size of the page also matters. Same story can be printed into different size of books, with A4 or A5 pages. As a result, the book would look larger or thicker, but the number of the words in the story would not change. But typically, if you begin writing in a specific size, changing the page size middle of the story would be a big hassle, as the paragraphs can get messed up. When I talk about database pages, the concept is similar. Each page contains data of one or multiple database objects. New objects are either written to the end of a page if there is enough space, or a new page is created. To track an object position, all we need to know is the index of the first byte within the whole database file. Then we can divide that number with page size, move to that page, and grab the object. Therefore, we can reuse our pointer class here as well, to point to the data in the database. If we create multiple files, we can also use the chunk property of the pointer class. To remember the pointer concept, you can check episode 4 of this series. Whenever we store an object to the database, we should input a byte array, and the output would be a pointer to that object. Of course, we could wrap that object with some metadata, but the core concept would remain the same. Also, when we store data, to know where is the last page, we can simply use the division of the file size and page size. But we need an additional metadata, which shows where is the cursor at each page. This cursor helps us to always write the data to the end of pages. So what happens when we want to remove an object? Unlike the story writer example, we don't care about the order of paragraphs in our book. As a result, we can remove the objects from any pages. The removal process could be the replacement of the object with an empty byte array, or just simply using a bit flag system in an object wrapper. But we cannot shift back the remaining objects within a page or whole database after removing an object, since that would mean all the pointers to that object should also get updated, and we simply may not know where the pointer is used. But then what happens if we remove too many sequential objects? Can't we somehow reuse this space? Since the order of objects don't matter to us, we can implement a mechanism to track removed objects by storing the pointer and the size of the removed object. When a new object is about to get stored, we first search to see if we have any space for it in our removed objects. I won't dig deeper into this mechanism, but it certainly helps reducing the unnecessary growth of the database file.
The algorithm that we'd want to use to store data in the database is page buffer. So far, you've understood what a page is, so now let's join it with buffers and see how we can improve the performance. Our two primary operations on the database are reading and writing. We have discussed about the challenges of reading and writing into the same file in previous episodes when we talked about index storage managers. But we didn't implement index storage manager with page buffer algorithm. And things are a little bit different here. By the way, we can use this algorithm to store indexes in the database file as well, and not separate the index files from data files at all. But we won't focus on that in this video. Imagine our only operation is reading. As previously mentioned, to read data, we first go to the page containing that data. In a multi-thread environment, each thread may want to access different or same pages. Now here is where buffers come to the rescue. If a thread is requesting a page that is already loaded by another thread, instead of loading the page from disk into RAM one more time, we use the preloaded page. How? You guessed it right. Using cache. And to be more specific, we use LRU cache. I have briefly talked about LRU cache in episode 7 as well. To recap, a LRU cache is like a limited queue, and objects that are loaded to memory would be added to the queue to be cleared from the memory once the queue is full. Whenever an object is reloaded from the cache, it will be moved to the end of the queue. Therefore, the least recently used object would be ready to get out of the cache. Also, if you remember file handler pools from episode 6, we keep a counter to know how many threads a page is referenced in. We would not let go of a page until the reference count decreases down to 0, even if the LRU cache gets full. If the page is requested again before the reference count is 0, and after it's removed from LRU cache, we should add it back to the cache. Of course, we should limit the number of pages we store in memory outside the cache in order to prevent loading all of the database from disk to RAM. Now let's see how the write operation may work. Generally, threads would be able to change a portion of a page to either update or write a new data. Since we load a whole page into memory and track the references, a page could be queued to be committed to the disk. In other words, pages get loaded into the buffer, and multiple threads may modify different sections of the page. But instead of running multiple write operations on the file, we rewrite the whole page into the disk. You may wonder, what's the benefit of this approach? Considering the fact that pages are within the buffer, and we have multiple threads that do both read and write operations, a change within the page is immediately visible to readers before it's actually committed to the disk. However, the disadvantage of this approach is that the state of the memory and disk would be different. Therefore, reader threads may access a data that is changed on the RAM, but not on the disk yet. In case our application crashes at this state, before committing a changed page to the disk, it is likely to have caused bugs and issues in the system. That's why most databases use different approaches, such as operation logging, to recover to a valid state before the database starts again after a crash. But that may be the topic of another video. If you want to see the current state of my page buffer implementation, check the repository. You can head to the storage package, then to the DB package, and you can find classes such as page, page buffer, and DB object. The link to the repository is in the description. As always, remember that the project is still ongoing and there may be some issues in the code. If you spot one, open an issue on GitHub. I would appreciate it. Thanks for watching the video. I hope it was helpful. If you find the channel and playlist helpful, please consider supporting my work by liking the video and subscribing to the channel. You can also support me through donations, which helps me spend more time creating educational and experimental contents. See you in next video and take care.